Swayam Prabha. Digital India. Educated India.
Welcome to lecture 16. Today we are going to talk about the unique factorization domain. So let's start. So before defining what is unique factorization domain and why we are looking for it, let us get the motivation from the ring of integers. What do we have seen in the ring of integers? So we know that in Z, if I consider n is any integer in Z, then this integer can be written as product of prime element. So, if then every integer that n can be written as product of prime elements. So, that is something that we already know, and this n can be written in a unique way as product of prime elements. But then we thought of instead of just looking at the ring of integers, can we say something about in general. So, if you start with any ring and then you pick up any element, whether you can say something about whether we can write down every element in a ring as a product of prime elements or something similar to that. So, for that we need to define first what is the notion of prime element in an arbitrary ring, and whether it can be written uniquely or not. So, in order to answer those questions, this notion of unique factorization domain comes into picture. But before defining it properly, let me first define couple of terms. But now onwards, from today's lecture onwards, we will always assume our ring is an integral domain. So, let me just write it down. So, from today onwards, we assume our ring are integral domain. So, integral domain is one of the basic property that we need in order to do all this kind of factorization and all. So, from now onwards we will assume all the time our rings are integral domain. So, now let us define some of the terms. So, first of all, when do we say that an element divides another element? So, we say an element A divides an element B divides another element B, which is denoted by this symbol A divides B, if I am able to write down B as multiple of A. That means, if I am able to write down B as B equal to A into Q for some Q in R. So, R is an integral domain and we are saying that an element A divides another element B if B can be written as multiple of A. So, this is definition 1. Then I am defining a proper divisor. So, the element A is said to be a proper divisor, is said to be a proper divisor of B if neither A nor Q is an unit. That means whenever I am writing B as multiple of A, in that case neither A nor Q is a unit. Then we say that A is a proper divisor of B. Next, I am going to define an irreducible element. So, we have already talked about irreducible polynomials. Now, I am going to define irreducible element, which is the generalization of irreducible polynomial. So, an non-zero element, a non-zero element A of an integral domain R is called irreducible if it is not an unit, if it is not an unit that means A first of all is not a unit element, then only we can talk about its irreducibility. So, if it is not an unit and has no proper divisor What does that mean? That means if I am able to write down A as multiple of two elements, say B into C, then either B or C has to be a unit. Then either B or C is an unit. So, that is, it says an element is irreducible. That means you cannot write it as product of two elements, neither of which is a unit. So, in that type of elements are called irreducible elements. Next, we will define when two elements are called associates. So, two elements, say A and B, are called associates if I can write down one of the element as multiple of the other element B, where U is a unit. So, if I am able to write down one of them as a unit time other, where U is an unit. So, two elements are called associates if U is for some unit U, if I am able to write in this way. So, these are the couple of definitions which we will be using now onwards, and if I try to write down this definition in terms of using the notion of principal ideal, then we get the following statement. So, let me list down all this definition in terms of if I write down the definition or transform this definition using the principal ideals, then we will get the following proposition. What does it say? So, it says that let R be an integral domain. So, let R be an integral domain and I have say two elements A and B in R. Then it says, the first one say that A is a unit, A is a unit if and only if, unit in R, maybe I should mention that, unit where A is a unit in R if and only if the ideal, principal ideal generated by A is nothing but the unit ideal. So, which is equivalently saying that A is a unit element. Now, if I would like to say that A divides B, A divides B if and only if I am able to write down B as a multiple of A, right. But B as a multiple of A implies that B belongs to the ideal generated by A. That means the ideal generated by B is sitting inside the ideal generated by A. So, this inclusion says that B belongs to the ideal generated by A, and hence B can be written as multiple of A, which is same thing saying that A divides B. Now, we say that A is a proper divisor of B. A is a proper divisor of B, that is in terms of principal ideal, saying the thing that the ideal generated by B is strictly contained inside the ideal generated by A, and which is not the unit ideal. This implies that A is a proper divisor of B. And we say that A and B are associates. A and B are associates if and only if. That means, in that case I will be able to write down A as some unit times B. So, that means the ideal generated by A, the principal ideal A is same as the principal ideal B, because A can be written as U times B. So, A belongs to the ideal generated by B, and again B can be written as some unit times A, therefore, these two ideals are same. And the last one says that A is irreducible if and only if. First of all, irreducible means it has to be a non-unit element. That means this ideal should not be the unit ideal, and so, or other way I can say that this has to be a proper ideal, which should not be the unit ideal, and also that there is no principal ideal, and there is no principal ideal C such that this A will be strictly sitting inside C, which is not the unit ideal. So, A is irreducible means what? A should not be, I should not be able to write down A as product of two non-unit elements. So, if A is sitting inside C, that means that I will be able to write down A as product of two non-units elements. So, that will contradict that A is irreducible. So, the irreducibility condition is saying that there does not exist any, this is very important, principal ideal generated by C such that which will contain strictly this ideal generated by A. That means, this is in some sense maximal in the chain of principal ideals. If A is irreducible, then that should be the, if I consider a chain of principal ideals, then that ideal generated by A should be the maximal element in that chain. So, that is what it says in terms of irreducibility. Next, we will prove that what is a prime, next we will define what is a prime element. So, the next definition is a definition of a prime element. So, we say an element A is prime if the ideal generated by A is a prime ideal, if the ideal generated by A is a prime ideal. So, we have now generalized the notion of prime elements to any arbitrary ring. So, in the ring of integers, we have this notion of prime integers. Now, if we have generalized it to the concept of prime element, when we say an element is prime, if the ideal generated by that element is a prime ideal. So, now we will see the relation between an irreducible element and a prime element. So, is every prime element is irreducible, or is every irreducible element is a prime element? So, let us try to investigate. So, we will first prove that every prime element is irreducible. It does not matter which ring we are in, it is always true. So, first we will prove that let R be an integral domain and I have a non-zero element say A in R, and if A is a prime element, then we will show that A is irreducible. Then it is irreducible. That means prime elements cannot be factored further into product of non-identity elements. So, let us go through the proof. So, it says that since A is a prime element, this implies that by the definition the ideal generated by A is a prime ideal. So, this is a prime ideal. We want to show that it is irreducible. So, that means if I am able to write down A as product of two elements say B into C, then I have to show that one of them has to be an unit. That will prove that A is irreducible. So, if A can be written as B into C, then this product BC belongs to the ideal generated by A. So, then as A is a prime ideal, this will imply that either B is in the prime ideal generated by A, or C belongs to the ideal generated by A, because the ideal is a prime ideal. So, if we assume, suppose that without loss of generality, we assume that B belongs to the ideal generated by A. This implies that I should be able to write down, since B belongs to A, I should be able to write down this B as some multiple of A for some D in R. Now, if I replace this B in this expression here, then what do I get? So, we have now that A equal to BC and B is equal to AD. So, I have got ADC. So, from here I can take out A and I can write down there DC minus 1 is equal to 0. Now, this is an integral domain and A is non-zero. So, since R is an integral domain and A is a non-zero element, this implies that DC minus 1 is equal to 0, which says that DC is equal to 1, which implies that C is a unit. This implies that C is an unit element in R. So, I am able to show that whenever I am writing this A as product of two elements B and C, then one of them is becoming an unit element, therefore, A is irreducible. Therefore, A is irreducible. So, we have proved that in an integral domain, every prime element is irreducible. Now, let us go to some example. Suppose we are in Z, the ring of integers. So, in Z, if I look into a irreducible element, so that irreducible elements are what? Those elements which cannot be factored further. So, those elements are nothing but the prime numbers, right. So, therefore, in Z, irreducible elements are prime elements also. So, in Z, every irreducible element is prime, which are nothing but the prime numbers. Now, if we go into the polynomial ring over a field where K is a field, then here what we can see that if I consider an irreducible polynomial, then that ideal generated by that polynomial gives you a prime ideal, because we have seen that irreducible polynomials always generate a prime ideal. So, in this case also irreducible elements are prime elements. So, in this ring also irreducible elements are nothing but irreducible polynomials and the irreducible polynomial generate prime ideal. Therefore, irreducible elements are prime elements. So, then you can think of, okay, we have this ring of integers z, and also in this polynomial ring over a field we have observed that every irreducible element is a prime element. Then you can ask whether it is true in general. If you start with any integral domain, is it true that every irreducible element is prime? So, that is where we ask the question that is every irreducible element in an integral domain is prime element, because the previous two cases says that yes, in these two cases at least it is true, but we will see that it is not true in general. So, let us go to the example where it is not true. So, the example that we are giving, so consider the following ring. Consider this ring R, which is z square root of minus 3. What is this ring? How does the elements look like? So, the elements of this look like nothing but a plus square root minus 3 into b, such that a and b are integers. You can check with respect to this addition and multiplication. This is in fact a subring of the ring of complex numbers. So, this has a ring structure, and in this ring we will show that every irreducible element is not a prime element. So, for example, let us consider the element 2. So, consider the element 2. So, of course, 2 is an element in this ring. Now, okay, so here we will show that 2 is an irreducible element, but not a prime element. So, first I want to show that 2 is irreducible. So, if I want to show that, then let us say that 2 can be written as product of two elements. Say let 2 is a plus ib square root 3 and c plus id square root 3. So, I have written 2 as a product of two elements in R, and then we have to show that if 2 is irreducible, then one of them has to be a unit. That is what we need to show. Now, if what will be my 2 bar? 2 bar is nothing but the complex conjugate. So, 2 bar is equal to same as 2, but this is a minus ib into c minus id. So, then 2 into 2 bar will be nothing but a square plus 3b square into c square plus 3d square, but 2 into 2 bar is nothing but 4. So, therefore, this implies that this a square plus 3b square must divide 4. What are the divisors of 4? It can be 1, 2 or 4. First of all, note that a square plus 3b square cannot be 2. Note that this a square plus 3b square is not equal to 2, because a and b are integers. For no integer values of a and b, it can be equal to 2. Therefore, the choices for a square plus 3b square is either 1 or 4. So, let that a square plus 3b square is equal to 4 if it is 4, then c square plus 3d square has to be equal to 1. But c square plus 3d square is equal to 1, this will happen only if c square is equal to 1 and d is equal to 0. That is, c is equal to plus minus 1 and d equal to 0. So, in that case, what is happening in this expression of 2, I can see that this becomes the multiplicative identity, that means unit element. So, if I am able to write down 2 as product of 2 elements, then one of them is becoming unit, therefore 2 is irreducible. So, here we are able to show that none of the here we are able to show that this 2 is irreducible, because one of the factor of 2 is always the multiplicative identity 1. So, we are able to here proved that 2 is irreducible. Next, we will prove that 2 is a prime element. So, next we will prove, so next wants to show that this is a prime ideal. Sorry, this is not a prime ideal. I will show that this is not a prime ideal. Here we are actually giving a counter example. We are showing that not every irreducible element is a prime element. So, here we will show that 2 is not prime ideal. That means, it is not a prime element. So, for that what I will do is that, note, if I consider this product of 2 elements, 1 plus square root of minus 3 into 1 minus square root of minus 3, which is nothing but the element 4, which belongs to the ideal generated by 2. 4 belongs to the ideal generated by 2. But here we can see that none of these elements belongs to the ideal generated by 2. Therefore, I have seen that product of 2 elements is in this ideal, but none of them is in that ideal. Therefore, 2 is not a prime ideal. Thus, this is not a prime ideal. And why it is happening here? You can see that this element 4 has 2 different factorization. This 4 can be written as 2 into 2, and this can also be written as 1 minus root 3 square root of minus 3 and 1 plus square root of minus 3. So, we have for the same number I have 2 different factorization, and that is creating the problem. And from here we are defining the notion of unique factorization. So, let me give you the definition. Formally, what is an unique factorization? So, a unique factorization domain, we will write in short UFD always. So, a unique factorization domain is an integral domain R which satisfies certain properties. What are the properties? Satisfying the following properties. What are the properties? So, the first property says that every non-zero element can be written as finite product of irreducible elements. So, every element, non-zero element in R can be written as product of irreducible factors say P1 up to Pn up to a multiple of unit, namely I should be able to write down A as some unit time P1, P2, Pn, where each of these Pi's are irreducible elements in R. So, this gives you a factorization, and unique factorization means this factorization should be unique also. So, what does that mean? That means that the above factorization is unique. That is, if I am having two different representations, so suppose A can be written as some unit times P1 up to Pn and some unit times V into Q1 up to Qm, where these are two factorizations of A into irreducible factors, or are two factorization into irreducible elements. That means this Pi and Qj are irreducible and these U and V are units. So, if I have two different factorizations, then they are related in the sense that then I should have that the number of irreducible factors should be same, that means n has to be equal to m, and moreover this Pi is associated with some Qj. This Pi is associated with some Qj. So, first of all, unique in the sense that all these numbers of irreducible factors has to be equal and this Pi has to be associated with some Qj. So, let us see just quickly one example. What do I mean by they are giving the same factor uniqueness? By uniqueness, what do I mean? So, in Zi, if I consider suppose the element 5, so 5 I can write it as 2 plus I into 2 minus I. This I can also write it as 1 plus 2I into 1 minus 2I. But this gives the same factorization because these two are same factorization because we will show that if I multiply by this unit minus I the element 2 plus I, then I will get 1 minus 2I, and if I multiply I with 2 minus I, then I get this element 1 plus 2I. Therefore, this element 2 plus I and 1 minus 2I are associates because one of them I have written as some unit times the other one. So, here these two gives the same factorization because these are associates. So, this is in fact the same factorization, this factorization is unique in this way. So, that is what I wanted to mean by the uniqueness of factorization. So, today I will stop here. These are the references that I have used for today's lecture, and thank you.